I'd like to thank Garrett for the invitation to this wonderful place. So in the next hour, I'm going to tell you about our study on cavity electrodynamics of Magnons. Again, my name is Tang. I'm a professor in electrical engineering at Yale. I also carry the hat, physics and applied physics appointment. Here's my group website. Our group name is Nano Devices. I will show you in my talk, none of our devices actually in the context of Magnon is nano, so they are relatively big. So let me start talking about the material. Our favorite material to study Magnon is yttrium iron garnet. Has been covered yesterday by a number of speakers. So we really like Magnon, not only because it has magnetic property, it's also because it's optical properties. So it can be made into a thin film. You look through that, it's transparent, a little bit yellowish because of dopants. So the application of YEG is very vast. You can find they are used in many microwave devices as filters, as delay line, as isolators. They're very powerful. So they also use the optical isolators. If you go to Thorlabs, go to the website, you can buy these optical isolators. It's based on garnet. So in the semiconductor world, in the photonic world, people have been developing garnet film on silicon photonics devices to make sure the light that can go in one direction, which is very critical for laser applications because you don't want laser come back to spoil your cavity. So here's a typical device that we study in our lab. It's a piece of garnet. It polished into a very smooth sphere. The smallest one we can make is actually shown over here. So this is a fiber. Diameter is about 125 micron. So this diameter of this specific sphere is about 250 micron. This is the smallest one we can glue and handle in our lab. So we know that when you polish this into sphere geometry, this sphere will support different mode of excitations. Apparently, the mode we are most interested in is this Magnon mode. Those are collective excitation of spins inside the sphere. You could have a different kind of order of whisper gallery mode. And the most common mode we study is this uniform mode. Apparently, there are other modes there. So we have a sphere in the photonics community. Apparently, you have all those different optical whisper gallery mode. And you can index with an NLM, different mode index, and different polarization. So I show over here, it's called the TM polarization and the TE polarization. And what's probably less known is back in the 60s, 50s, people study garnets for its mechanical property. It's a very hard gemstone with hardness of 9, diamonds 10. So when you have materials that are hard, most likely it has a very low mechanical loss. So if you polish a sphere, if you support very nicely, you can have a quantity factor, mechanical quantity factor up to a million. So there is acoustic kind of whispering gallery mode inside this sphere. So this is a very simple structure. You have 3 different excitations, and they couple they can couple very strongly. And that is sort of a context I'm going to discuss. I'm going to tell you about the interaction of a magnon between two light and two photons. You may be wondering that the magnon operate like oscillation is about typically gigahertz and to tens of gigahertz. And optical mode, we work with telecom wavelengths. It's around 200 terahertz. So acoustic mode slower, and anywhere from 5 megahertz to 30 megahertz. So their frequency are vastly different too. So how do you couple them together? So here is two different processes I like to discuss about. So you have, so let's just look at the two different modes. There's A mode and a C mode. It could be either of these two excitation, microwave photons, magnon, optical photon, and acoustic photons. So this A and C could be any two of them. So you want to couple them together. Their resonant frequency could be the same. When their resonant frequency is the same, the coupling normally you have a dipole coupling. For example, the magnetic field component of your microwave coupled to the magnon is a dipole coupling. So here, in terms of Hamiltonian, this is so-called a bilinear coupling. So this could be a native magnetic field and the magnon field. So they couple together. So this interaction, I call it Chi-1 process. It's a really direct dipole coupling. What do you think about in terms of optics? Like this coupling change your dielectric constant. Okay. So that's what's the Chi-1 process. So the same process describe two harmonic oscillator coupled together. So two spring coupled together or two LC resonator mutually coupled together. You have a hybridized mode when you have a frequency degenerate. And the same process describe a piezoelectric field effect. If a mechanical motion of in a piezoelectric material, you shine microwave on that piezoelectric material, that's the same type of coupling. Okay? And also electromagnetic coupling, you basically eliminate your X sphere with microwave, and that's that type of coupling. Everything's linear over here. Okay. The second type of coupling is really at the core of my discussion today. Is this kind of a nonlinear coupling, three-wave like mixing type of coupling. So what you have, if you think this two mode is like a more common study like optical mode and a mechanical mode. So this is like a displacement over here, X. And that's like a force. So that's a radiation pressure force that proportional to the number of photons, and then that's the displacement. So this process describes a lot of physics. There's a Raman scattering, the Brion scattering, and moving capacitor. If you have LC circuits, this capacitor moving, same describe that process. Okay, so two excitation of very different frequencies, they couple together through a three-way mixing process. So you have a parametric pump. And electro-optic modulator also described by that process. You send a microwave to drive the optics and send a light through the fiber network. And the Faraday effect, which is closely related to the non-reciprocal light propagation in the YIG. And they all come from what I call engineered Chi-2 effect. So take home the message that there's a linear coupling, is Chi-1 process, and this nonlinear coupling, a radiation pressure-like coupling, is Chi-2 process. So if you put the Magnon at the center of the stage and look at their coupling to the microwave photon, optical photon, and photons, so the Magnon coupled to microwave photon is a Chi-1 process because most likely their frequency going to be same. But that's not the only process existing in YIC. There are other higher order coupling. There are also Chi-3 process, which is a Fourier mixing. But that's relatively weaker in our discussion. The frequency range is very interesting. In the Magnon to photon coupling, it's Chi-2 process. It's like radiation pressure coupling. And same thing happen with Magnon to optical photon coupling. So this coupling system exhibited a lot very less coherent behavior. There's strong coupling happening between those different excitations, in particular for Magnon with a microwave photon and a photon. You see, that's why this arrow I'm showing over here, they're solid arrow. That means we realize the strong coupling. But this arrow connected to the optical photon is dashed. That means we're not there yet. Okay. So all these optimakanaka tricks you can play among those degree freedom. You have a magnetic induced transparency, cooling of a mechanical resonator, parametric amplification of a Magnon, photon lasing, microwave amplification. Most importantly, is this microwave to optical conversion really that motivate our work back in about 9 years ago. So I really like to focus on discussion centered on this topic and how we engineer and control this device for that application. So here, basically the 4 topics I'm going to talk about, I already briefly talk about is the Chi-1, Chi-2, Chi-3 process in those different excitations. And I will start talk about really what enabled how you access Magnon. This really rely on this branch over here, this Chi-1 process. Then I move on to this coupled to photon, this Chi-2 process, and to optics. So microwave to optical conversion. For those of us working in the field, we know there's 2 types of quantum optics that are being working on. In the kind of working with a different color of photons. There's one community which advanced very far is there's quantum optics based on microwave photons. There's another community work on so-called quantum optics that work with real photons. And so this, I'm coming from Yale. Yale has really a leading group work on these circuits of microwave photons that lay down the circuit with superconducting thin films like aluminum. What's really nice, when you work with a photon that has a wavelength of centimeters, and you can build an atom that has a really large antenna and have a single photon nonlinearity, which is just in junctions. And they can form different qubits. And one very nice qubit was a transmon qubits that have been developed at Yale, and that can perform a very high power quantum computing task that it can involve 2 qubit gates with 1 qubit to control other qubits. You have very high coherence. A lot of wonderful things happening in this platform. The real limitation of this platform that you have to work out a millikelvins. Their effort try to make a very long superconducting cable to send the quantum information out. Again, your cable has to be superconducting, and that's really hard. There's a limited distance you can send your signal out. Whereas in the optical domain, my group have been working on different quantum optics, deal with the single photons. The problem is, all those photons did not have a deterministic operation, okay? Everything based on post-selection. So you do not have a single photon nonlinearity like what you have with Josephson junctions. But what you have are the room temperatures that the light there's no decoherence to the light. The fiber can propagate light with a 0.2 dB per kilometer. Okay, so you can send information to very long distance with all those billion-dollar existing telecom communication hardwares. So apparently then that produced a third community try to work them together, to make them work together, connect them. Try to convert a photon from a microwave domain to optical domain. Okay. It is hard. It's hard in a way that the superconductor and the light do not like each other. Okay. You shine light on the superconductor, you produce a lot of quasi-particle. You can even kill the superconductivity. Okay. And the superconductor absorbs light. So, and also, the frequency differ by 4 order magnitude. So you are trying to convert a photon with a 10 gigahertz photon, which has energy very, very tiny optical photon. So we know optical photon is an EV. So microwave photon is, you have about 100 micro EV of energy. So there's huge difference in energy. So what do you mean convert a microwave photon to optical photon? So what we are talking about is really not try to make the energy conserved. We just want to change the carrier. So the same thing you do in the radios, you modulate a carrier in the IQ space. There's a positive elective part of this regular function, whatever how you can describe your statistic of your photons. What you want to do is that you do not want to change your statistic property of a photon. Okay? What you only want to change is the carrier frequency. You up convert, down convert, but your sideband or your Wegener function remain the same. So there are a lot of different approaches in the community try to make this happen. Or there is one approach that exists for decades, 100 years, is electro-optic modulator. And we're using it every day. We receive our email from somewhere other side of Earth. It's really rely on this long-haul application of this electro-optical modulator. You send a microwave to those connectors, the optics get modulated, create sidebands. It's a very low efficiency, on the order of 10 to the minus 7. Okay? As you can imagine that there's a lithium niobate crystal, which is about 6 centimeters long. If you make an optical resonator instead of use a straight waveguide, you can enhance your coupling efficiency. And that was done in this paper. But 2 years ago, Optica, they can improve the efficiency by 4 order magnitude. Just use an optical resonator to enhance your coupling efficiency. You can do that. What you really do is you don't gain too much because there is always a bandwidth gain kind of a limit. So what you do is you use an optical resonator, like lithium niobate disk. You reduce your bandwidth. This device have a 40 gigahertz bandwidth or 50 gigahertz bandwidth. If you reduce the bandwidth by 3 order magnitude, your efficiency go up by 3 order magnitude. That's actually what can be done. Fortunately, in quantum information processing, we're not talking about 40 gigahertz bandwidth. We're talking about 10 megahertz bandwidth. So there's a lot of places you can sacrifice your bandwidth. And this is our paper. We just put on archive last weekend. Check it out. We're really excited about this result. So now, instead of partishing the lithium niobate into a disk, you make a little tiny ring resonator here. Then you put a microwave resonator on top. This looks like a goldish, but it's actually niobium tinitride, which is a superconductor. And there's a reason we designed this superconductor looks like the symbol of infinity. It has infinity power. It is a special resonator that allow us to phase match the microwave to optics down there. So the microwave and optics can couple in the near field. So optics are inside the near field of a microwave. Microwave is not in the near field of optics. If you do that, you'll kill your superconductivity. So we are able to engineer this device to achieve 26% conversion efficiency from a microwave to optics. So this is what we like to achieve with Magnons. And I will tell you where we are and how far away from here, this electro-optic device. So that basically tells you that an electro-optic modulator is the same as a Magnon optic modulator. The difference is that you work with the electric domain or magnetic domain, okay? The magnetic domain has benefit that you can tune the resonator, okay? You can just change the bias field, your resonant frequency can change the arbitrary frequency. The disadvantage is that your magnetic interaction, magnetic dipole, always weaker than electric dipole. And that's the battle you have go against. Another issue is that your electro-optic material, pockets material, lithium niobate, or in this case we use aluminum nitride, and those materials are highly perfected material. The optical loss in those material like dB per meter, okay? And our YIG, we're talking about dB per centimeter. Again, there's order of magnitude improvement that needed to be done. Okay, there are other approaches to do this microwave to optical converter. There's uses this tiny membrane, silicon nitride membrane plate that was pioneered by my colleague Jack Harris. I've been really done worldwide. The idea is that you have this membrane on one side is coupled to a microwave cavity, another side is coupled to optical cavity. You mediate this conversion between these 2 degrees of freedom. And that mechanical resonator is on order of a megahertz. And in my lab, we also work on mechanical resonators at around 10 gigahertz to start with. It's a tiny, tiny disk that's about 6 micron in diameter, made of a piezoelectric material. Through Chi1 coupling to the microwave and Chi2 coupling to the optics to do the conversion. This also promised to be very nice converter because of the mechanical resonator work at 10 gigahertz to start with at the dilution refrigerator temperature via the ground state. So there's no noise added to the system. With the membrane, even at 10 millikelvin, you already have 1,000 excitations, thermal excitation over there. So there is a pro and a con. This is a very nice coupling. This is a coupling a little bit weaker, but you do not have that noise problem that you have to worry about. Okay, let's go back to this YIG. As I mentioned, that you're using polarizable material, which has the benefit of you have a collective coupling. I'm showing you here there's a multiple pathway you can have a microwave to optical conversion. Electrical optic, direct pathway, there's no intermediate media. And we show that maybe that's still the best approach. It has been the best approach for the past 50 years. It's probably still the best approach to get a microwave to optical conversion. But this is what we have tried, and the photon and the Magnon approach. you have an intermediate converter to mediate that. And that's what I'm going to talk about most of the time, and because that's where we start with. So I mentioned those Chi1, Chi2, and process. So Chi1 process is just a linear process hybridization. Chi2 process is thorium mixing here. All this effect over here. There's also Chi3 process. If you're familiar with the frequency comb, that's a Chi3 process. And a Magnon, you have a foil mixing. It gives you the Schulze instability. That happens too. Those also happen to the frequency of the same carrier frequency. I should emphasize that if you combine those processes, you can have different kind of engineered Chi2 or engineered Chi3 process. For example, if you combine one Chi1 process with Chi2 process here, combine this one and this one, you have effective stereo mixing here like this. And these actually describe the Magnon mediated microwave to optical conversion. Okay. So there need to be a pump. There need to be an optical pump in that process. So if this become an optical pump, go backward, you have one mode to convert to other mode. That's your control beam in atomic physics picture. You also can combine two Chi2 process. Okay, combine these two. Eliminate this is the one. You get a stereo mixing. So in stereo mixing converter, if you can convert from here to here, you need a two control beam. You need a two pump. So that's a difference. So for the membrane device, I'm showing earlier, this one is a three-wave mixing. So you need a two pump. Where's the two pump? One pump you apply to the LC resonator. Another pump you apply to your optical resonator. For all the other device, electro-optic device, magneto-optic device, they involve only one pump. And that pump is to control your coupling. You turn the coupling on and off. Okay, so now, because the photon and Magnon are really the same thing, and I'm just going to connect them together. So when you have a direct electro-optical conversion, remember you have this radiation pressure like a Hamiltonian. In a rotation wave approximation, you can linearize to this bilinear Hamiltonian. You look at the optical field fluctuation. You can enhance the coupling, which is proportional to the square root of photon number. So enhanced by your pump intensity. And for these cascade process, the first step, you could have a Chi1 process. For example, you have a piezoelectric material that's a Chi1 process, or a Magnon that's Chi1 process. If you involve kind of a membrane, that's Chi2 process. Either way, you can have this bilinear Hamiltonian. For the membrane, you need to do the rotating wave approximation. Here you're enhanced by the pump photon number. Here, same thing with this radiation pressure-like coupling. You can write it in the bilinear Hamiltonian. So you basically unify this coupling term. Everything can be rewrite in this kind of a bilinear Hamiltonian in a rotating wave picture. Okay, you rotate the pump out. So that makes your theory analysis very, very simple. The picture over here is pretty straightforward. So in the EO converter, you have one pump that make up the difference of a frequency from a microwave and optics. You have a quadratic coupling Chi2 process. With that membrane-mediated process, you have a two pump. That's a foil mixing process. Okay, 2 pump, 2 signal. You do that same thing in a fiber. You do it with the optic and a microwave. With yttrium iron garnet, a little bit different. Here is linear coupling. Here is mode splitting direct coupling. But essentially, you only need 1 pump. You convert the one with the hybridized mode to the optical mode. So with like piezoelectric, like aluminum nitride resonator I showed you earlier, is the same thing, same process. So, so electro-optic conversion is very easy to model. That's been done in the community, cavity optical mechanics. With it's a photon Magnon mediated process. Now you look at the coupling system. The intermediate excitation couple to the input and output mode through electromechanical coupling and optomechanical coupling, or electromagnetic coupling or optomagnetic coupling, same thing. Okay. So 3 modes, and each of these modes couple to their own environment reservoir. You can model by a dissipation rate and the input-output mode. So you have all those modes, and you have this reservoir mode. You can write this input-output theory. So you have input microwave mode, input optical mode. You have a 3 dissipative mode over there. That's act on your input. And then the output mode over here, output microwave mode, output optical mode. And you have ACE matrix, 2x5 matrix. So you eliminate this intermediate mode. You can work out the input-output. I'm just giving you the result. S21 or S12, which describe the transmission of this accompanied system from here to here or from here to here. And that actually very simple Lorentzian transmission shape. So this delta omega is detuning of this mode. So if all 3 modes on resonance, the delta omega is 0. So this term disappears here. And this W describes the impedance mismatch of the 2 coupling channel. So that's the effective coupling rate through this coupling channel. That's a G squared over the dissipating rate. So-called cooperativity, which describes the G squared divided by kappa E and gamma E. So that's related to ratio of two cooperativity. So you can see that if you want to maximize this conversion rate, you want the conversion to be unitary, 1-to-1, you need that you both resonate, all the resonator to be on resonance, 0 detuning, triple resonance. You need this W to be 1. You need the impedance on both sides to be exactly matched. Okay? So get a 1-to-1 conversion efficiency seems not be very demanding. Your W can be any number as long as they're matched. But that doesn't tell all the story. You still need this W to be 1. You also need this cooperativity to be much bigger than 1, because the cooperativity describes this gamma divided by intrinsic damping rate. So you do not want your noise from an environment to come into your system to spoil your conversion process. So you need this cooperativity to be larger than 1, so your noise added during this conversion process to be way less than 1 excitation. So because your added noise proportional to the thermal excitation of the environment divided by that cooperativity. So basically the requirement that you need both cooperativity to be much bigger than 1. You need them to be identical. So that is hard. There are also conversion bandwidths, which are really the mean of all those rates in your system. So an ideal converter would require the S21 or S12 to be 1. You want the cooperativity to be identical and bigger than 1. And you also need the bandwidth to be large. Okay. And typically for superconducting circuits, we need a transfer bandwidth about 1 megahertz. Okay, that's basically tell you about what is the consideration we have in mind to create this microwave to optical converter. The remaining part is really material and device engineering. I'm going to just go through that. So first, let me tell you about what happened in the magnetic system and how we engineer this linear coupling and this cubic coupling process, a quadratic coupling process. So let's first look at the Magnon to microwave photon process. This actually is the easiest thing to do, being done in the microelectronic world. So if you look at in the spectrum analyzer or electron analyzer, those old Agilent box, where they have this kind of a single one-turn antenna couple to a little sphere. At Yale, we have been working on this microwave cavities made of copper or aluminum. So it's very easy to make. You get a piece of aluminum or copper. You go to machine shop, dig a hole inside there, a rectangular hole, and you get a very nice cavity, a room temperature with a Q of almost 8,000. So you put a little sphere inside over there. So you look at your electromagnetic wave mode. Look for the magnetic component where you find a peak of a magnetic mode. You put that little sphere over there, and you get a strong coupling right away. Okay. So the coupling strength, again, is proportional to the number of spin inside of the EX sphere, which is plenty. Okay. Square root of n. And also invert to the mode of volume. So n over v matters. So if you have a sphere of like a 0.5 millimeter in diameter, put this centimeter size coffin, we call it a coffin cavity, you can get this strong coupling with a coupling rate of 11 megahertz. This coupling rate actually it can be arbitrarily big. So you can make a very tiny kind of a pea-size cavity. You can get the coupling rate of 2.5 gigahertz. So it's really very, very strong coupling. And it's very simple. You get the dipole coupling, and again, you see this Chi-1 coupling, and that's why it's very, very strong. So you can study the dynamics process. You threw a microwave photon inside of the cavity, microwave pulse. You can see the energy actually swap like back and forth. You can see these Rabi-like oscillations. So same as your coupled piston. So you push one, the other one pop up. When the other one drop off, this one pop up. So this happens. It can be smarter, and so you can put the two spheres over here. If they're identical, you have this dark mode here. Okay, the dark mode happens that the two spheres oscillate out of phase. Okay, so before you're detuned, you have 3 modes, but when you are 0 detuning, you have 2 modes left. So this is basically 2 spheres move like in synchronization. And you can think of this as this dark mode, which does not couple the cavity. The bright mode couple the cavity square root of 2 better, and you can use this dark mode as storage of your microwave photons. Of course, in the end, you're going to be limited by the intrinsic line width of your dark mode. You can also think of this in the time domain, and this is in collaboration with Florian and Lianjiang. These, you not only use 8 spheres, they're all identical. And we also bias each sphere have a different oscillation frequency. Basically, you build a gradient of oscillators you have a gradient memory. So you have this echo behavior. So after certain delay time, you can refocus your pulse send into the cavity and store in a time domain. So you can store in the temporary dark mode of this coupling system. And that in this paper. So there's a lot of things you can play with even this very simple Chi-1 coupling. Okay, let's move on, talk about the Chi-2 process. And particularly, I'd like to discuss this Magnon coupled to photons. So, so the photon has a special trait that you need to suspend your magnetosphere in a very specific way, okay? And there are different photon mode. And there's one special mode over here, what I call 1-2-1 mode. Okay. And that mode have, if you look at this direction here, look at rotating along this direction, you have a 2 peak and a 2 minimum. Okay. And along that direction, you have a 0 displacement over here and a 0 displacement over there. So when you glue your little fiber, you want to make sure you glue at a place that you have a minimum mechanical displacement. So you're not spoiling the mechanical Q. And this actually turned a very nice mechanical mode we're looking at. To excite this mechanical mode, what you're exciting, you're utilizing this magnetostriction interaction. Okay. So when you talk about magnetostriction, you have an anisotropy you need to worry about. And you need to pick the direction you want hold. This is little sphere, so make sure the magnetostriction to have a maximized mode overlap with a mechanical vibration on this direction. So this is a classical interaction that you have magnetization coupled to the string, okay? If you quantize, this is exactly the same Hamiltonian. You have displacement coupled to the Magnon number, which is M. So this is radiation pressure coupling, right? It's mechanical coupled to the radiation pressure of Magnon. Okay, so this quadratic coupling gives you the Chi-2 process that is mediated by another pump, which is another Magnon pump. So specific to this device geometry, there is an additional benefit of using this geometry that, as I showed you earlier, when you put a sphere inside this cavity, you have the mode splitting, right? This mode splitting. The splitting of this mode determined by the interaction strength between the cavity mode and the Magnon mode. So if you put the sphere at a different location, you have a different splitting. And at one magical position, this splitting match your mechanical mode, which is 11 megahertz. Actually, it's not that magical because you have your tunability. You can work out exactly 50-50% hybridization, or a little bit different 50-50 different hybridization. You can tune this gap over here, okay? That looks like a lasing action. It is. So you have a lower hybridization mode, upper hybridization mode. If you do a good job, you can have a lasing action happen. So this is splitting match the mechanical. You have a very, very nice 3 mixing that all 3 modes are in resonance. Each of these hybridization modes have a Q of about 2,000. And you have a mechanical mode have a Q of about 40,000. So you can do all this optomechanical trick we've been doing in the optomechanics community. Right now you don't really have opti, you have a Magnon. It's not a photon, it's a Magnon. And you can do all this cooling experiment. The cooling happens at a relatively low microwave power. And you can also have a heating, you blue detune, you drive the mode at the upper hybridized mode. You can have electromagnetic induced absorption and kind of inverse transparency. And you have actually also have a parametric gain if your energy gain from this coupling cancel your loss of this mechanical mode. You can have in the regime, in this region, you can have so magnitude mechanical gain. So those are described by this very simple optomechanical theory in coupled mode theory over here. If you forget about this coupling G term, this is a bit really simple reflection from a cavity. You have detuning, you have a loss term, you have a coupling term. But after you include this coupling term, depending on the sign of your detuning and the intensity of this coupling, you have this EIT behavior or this amplification behavior. So we actually can make a kind of a photon laser or Magnon amplifier by this mechanical device, mechanical degree freedom. For example, I'm showing over here. So you can drive at this mode, the upper hybridized mode. And if you put a proton at the lower hybridized mode, you can have a gain more than 25 dB. So you not only have a transmission better than your input mode, you actually have signal 25 dB higher than your input mode. So all energy comes from the parametric down conversion from this mode to the photon mode and the Magnon, this is a lower level Magnon mode. So it's an amplifier, a very good amplifier. So then the same thing applied to the coupling between Magnon mode and optical photon mode. This is actually a much harder problem to solve. With the Magnon photon coupling, the mode volume are matched. Whenever you have a mode volume matched, you have a strong coupling. Now, if you look at the photons and Magnons, their mode volume are not matched. So this is too big for light. It's a millimeter scale device. You light on a micron scale. So there is this is actually a bit exaggeration to look at the optical mode. The optical mode number is always like thousands, very large. And the optical mode only occupy a very small portion of this sphere. So you have a huge mode mismatch. Also, you really need to make this device to be very smooth. Make sure you do not scatter photons. This device does not scatter Magnon because Magnon wavelength is large. But the photon have a very small wavelength. It's about 700 nanometer in this device. So you need to make sure that your roughness on the order of a nanometer scale, you do have not optical loss. Another challenge is that the coupling of light to this high index material is not straightforward. And that's more like a technical problem. Most easiest approach is just to pull the fiber and to let the light come out of the fiber to couple to the sphere. But that really doesn't work in this case because your mode in the fiber have index of 1.46. And when you pull it, your index becomes even smaller. But this sphere have index 2.2. This sounds a small number, but in the optical world, this is like a really astronomical big difference. It's a huge difference. It's make very little coupling from fiber to the actual mode you want to work with. So we solve this problem by really fine engineer of this device. So you buy this super polished sphere from this company called Sphere. They said that super polished, not really super polished. Look at this like a moon surface. a lot of a mountain over there. So you really want to super polish, you got my graduate student now to do it. And she can polish everything to like atomic, not like nanometer smoothness. So if you use a fiber to couple it, you got a very low transmission here. You can see certain mode with a Q of 80,000. This insertion loss is 10 to the 5. So like you have a 50 dB insertion loss because the coupling is very inefficient. We actually always engineer our fiber to the best. We cut the fiber, make sure the evanescence mode come out of end of a tip and the couple there and pick up a larger piece of fiber. It's very hard to manipulate all the 3 degree of motion, 3 freedom to get it to work, but you can't get it to work. So a smarter way to do it is to use nano devices. So you make a nanoscale waveguide, silicon nitride waveguide, really nice. I have an index 2.0. You make one of this. You glue it up to a fiber, have very low insertion loss over here. Now you approach your sphere on top of this waveguide and couple to this whisper gallery mode of optical mode. Then you excite the Magnon mode with this tiny antenna, which is very easy to get a strong coupling regime. So now you have a hand-assembled microwave to optical converter. Microwave come in here, coupled to the Magnon mode over here. You send the light in here, create a sideband, and take it out. And that's you see through the microscope, okay? This is that circuit board here. This is a copper trace here. That's a little antenna over here, your microwave signal source. And that's your sphere. And that's the fiber that glues that sphere. And you don't see is the waveguide, cannot see with your eye. And that's glue the fiber over here. So now you have a very nice coupling from fiber to the waveguide to the sphere. And you get a very high Q too. Your Q approach a median. From TE mode and TM mode have a different mode. I call it a quotation mark because in this sphere, not really in the TE mode and TM mode anymore. They're different. So the both Q can be very large. And here's the Magnon mode, or different order of a Magnon mode. So if you scan through all those optical modes, apparently there are a lot of them, and you can find their phase matching conditions because you just have a millions of modes to work with. So those are highlighted mode, phase matched mode. You have a TE, TM, and one of this Magnon mode to be matched. Okay, this mode to be matched. And you can realize these 3-wave mixing phase matching condition. So that requires your azimuthal mode number to be added together to be 0. You need the polarization. You need to satisfy this polarization selector rule. And of course, your energy need to be conserved. So the 3 things need to be satisfied. And that's really dictated by this mode integral, which you have magnetization induced susceptibility to match the optical mode number 1, optical mode number 2. There's a Magnon mode coming to here. The non-reciprocity coming from this term over here. So you have a selection rule. You can only couple from a so-called TE-like mode to TM-like mode. So that when you have in the waveguide, you have a TE mode coming in, it becomes like a circular polarization in the sphere, which we call sigma mode. TM mode coming in, it can become vibration along this equator in the transverse direction. We call it pi mode. So your pi mode can only emit a Magnon convert to sigma mode, or your sigma mode absorb a Magnon convert to the pi mode. And that's what you see from as a result, you only see one single scattering sideband. That's what you see over here. So TE to TM, or TM to TE, you gain 1 Magnons energy. So you can have this converter over here. You drive with Magnon mode, you convert from TM to TE mode over here. That's your conversion over here. Here I'm showing the conversion efficiency 10 to the minus 3, 0.1% from optic to optics drive your control beam is a Magnon. So which sounds okay. Electro-optic modulator have 10 to the minus 3 efficiency. But if you really look at the microwave to optical conversion, it's 10 to the minus 7. That's not good. That's the same model we have our electro-optic modulator we used for 5 decades. So we need to improve that. I got 5 minutes left. I'm going to conclude. So I tell you about all this different coupling, and I remain to have this dashed line over here. I have a strong coupling between Magnon and a photon, microwave photon. I have a strong coupling between Magnon and optic and a mechanical vibration, but I do not have strong coupling between Magnon and optical mode. And this is a hard part. This has been realized in the cold atom system, but not in the solid state material. I tell you about this conversion efficiency or different pathway. Right now, with these membranes, you have a 10% to 11% conversion efficiency, which is published. There's an archive paper by Karen Nader group and Cindy Riedgau's group have about a 47% conversion efficiency. And they are able to reduce the photon excitation to 40. And we have this device have conversion efficiency anywhere from 2% to 26%. We do not, because we work at 10 gigahertz mode directly, we do not really have noise photon coming, at least theoretically. And here we are in the Magnon system. Our conversion efficiency, you just count the number of 0 I put over here, 10 to the minus 7. We're working hard, try to make this better, to improve beyond this comparable performance with electro-optic modulator to at least move to some of those numbers. The approach, the main way to do it, you can enhance your Faraday effect in the material. You can reduce the Magnon loss. And we think the most important is the device scaling. And I hope I convinced that throughout my tutorials, really make the device smaller is the key. And if you compare the device we have with the piezoelectric material, here's my scale bar. It's a 5 micron over here, and this is 100 micron over here. So the mode volume, this Magnon sphere is almost 500,000 times, like 300,000 times bigger than this structure. Same thing over here. This is my electro-optical converter. Here, this scale bar, I forgot this is 10 micron. So this mode volume over here is a ring. It's comparable to this needle disk. You need to get the mode volume to be small. And that's the reason we've been pushing very hard to make a waveguide out of a YIG to make a really small cross-section. And here is an example of a device we're trying to make. At least we have a scale bar as a 10 micron right now. It's not 100 micron. So much smaller. There's your waveguide made of a YIG. We also use a material approach. It's in collaboration with the Colorado State University. We're trying to make a tiny, tiny micro rings out of a YIG through kind of epitaxial approach. So it's complicated, all this coupling process, but you have a unified picture. We're actually pretty serious. We have a cryostat that have optical fiber. Many optical fiber go down to millikelvin stage. We have identified 1 qubit, 1 converter. Apparently that converter is not a Magnon right now. In this cryogenic electro-optical setup. to do this microwave to optical conversion. And again, this is many years of work. I would like to thank all the collaborators involved in this project. Listing their name over here, a number of them in the audience over here. Thank you very much.